So we're gonna talk a bit about wallets today. And this is, so from at this point of kind of the textbook that we're following, Mastering Ethereum, it's definitely going to get a bit more technical. And today is kind of like, actually last meeting you guys saw the graph and the queue. And I do need to, if there's anyone that's still confused about that, please let me know, because I can explain at the end of this. I felt really terrible because I felt like I did a bad job of explaining it. But yeah, so just a heads up, it's gonna get a bit more technical, but not really in the sense of like coding, but more in the sense of like actually what's gonna be, what I'm gonna be explaining. So, but don't worry, I'll try my best. So kind of the overview today, we'll talk about the types of wallets, wallet best practices, and you guys already kind of gotten familiar and kind of already messed with a wallet. We set up MetaMask for you, or you did yourself, because I don't need to know your seed phrase. And then we'll talk about how do you say that?
Oh, mnemonic.
Mnemonic?
Yeah, it's
Mnemonic code words. I was reading in my head, just skipping over what it was actually. Then we'll talk about HD wallets, which are just hierarchical deterministic wallets. And then we'll actually get to pass, but you guys can definitely read up on that, because that's a bit more than we can handle today. But yeah, reminder, hackathon, please come to the meetings on Fridays. Like Bennett does an amazing job of just walking through like some codes that are already out there. So, you know, it's crypto, everything's kind of open source. So you actually get an understanding of like, okay, some variable types and you know how like function works, but he actually puts it in context of actually contracts that have been deployed. So highly recommend you guys come on Friday, 7 o'clock, same time, same place. And so that's gonna be great. Let's jump straight to it. So what is a wallet? You guys should already know, since we've all made one, I'm hoping. But a wallet is just a software application that lets you interact with the Ethereum blockchain. It's like the interface, right? And so you're not actually like, if you talk to people that don't really understand, they'll be like, okay, well, how do I actually like, you know, move money around in this place? Well, it's like, it's your wallet. But the thing about wallets is it's not really like, you shouldn't think about it like your normal wallet where there's cash inside of the wallet. It's more of like a keychain. But before I go into that, like some of the functionalities that we've already mentioned before is that it controls access to your money. It manages your keys and addresses. It tracks the balance. That's how you can see the price of ETH, whether it goes up or down. I don't recommend doing that. And then you can create and sign transactions, which is the most important part about a wallet, because this is how I prove ownership. Because kind of like the who are you Satoshi Nakamoto test is, hey, can you actually move the money in Satoshi's wallet? If you can't do that, you're not Satoshi, because you don't actually have the keys, and to have the keys meaning you have control of that wallet. So that is why creating a signed transaction is really important. And next week is gonna be about transactions, so that's gonna be really fun. But like I mentioned, a common misconception is that people think like your Ether, your coins are all in like that wallet. Like the actual software stores your Ethereum, stores all your ETH, stores all whatever cryptocurrencies you have in that wallet. And that's just completely wrong. Like I've been stressing, it is just storing your keys. And this is true for all cryptocurrencies, as in your wallet is how you move the money around. All you're really saying is, hey wallet, can you move money? Can you move money from this address to this other one? And because you have your key, you can like sign that transaction that says, okay, cool, you are the person that actually owns this, but all of it is actually just stored on the blockchain. And like I mentioned, you can think of it more like a keychain if you want, just a whole bunch of keys in there. And John, this is actually going to answer your question. Where are you, John? Because you asked me. So John asked me at the end of last meeting, like Solana, because we talked about, what was last meeting about? We talked about cryptography and how you can like create how your private key is created. And then he said like, well, in Solana, you can have like one private key and you can create a whole bunch of addresses. And this is where this answer I can actually answer your question. So there's two types of wallets. There's non-deterministic and deterministic wallets. And we'll start with non-deterministic, and it's more like random wallets. So with a non-deterministic wallet, each key is independently generated for each address. Really, that's the way to think about it. So you're gonna have a whole bunch of you're gonna have a whole bunch of private keys, And when you set up your MetaMask wallet, you got a seed phrase, right? And so the way to think about this non-deterministic wallet is like you would have a whole bunch of seed phrases that you would have to remember and store. And so kind of like the acronym for this type of wallet is a Jabok wallet, just a bunch of keys. So you're just gonna have just a bunch of keys. There's no real correlation between them, right? And so this is an inferior wallet type, and this is being replaced by deterministic wallets. Like non-deterministic wallets were like the first type of wallets that, you know, were first used in ETH during like the pre-sale, Bitcoin when it first was created. And the reason why it's a bad, it's an inferior wallet type is because good practice in crypto, when you're just using funds and addresses, is that you kind of want to have a different address for different types of funds you're receiving. Here it says that you want a new address every time you receive funds. That's a bit excessive. You don't really want to do that. That's just a bit excessive. But you can't have a wallet for like, hey, if my family's sending me money, if I'm getting money from a job, or if I'm getting money from a hackathon. And the reason for this is because you kind of want to keep your privacy. Yes, the blockchain, yes, because it's on a blockchain and, you know, there's only addresses, it's only numbers, but someone, if they're smart enough, can really trace back to who you are and who actually owns that address if you're using it all for the same thing, right? And so there's already companies out there that do major blockchain and like analysis, and this is kind of how the government has actually tracked, like, I think it was, what is it? Some type of like malware where they'll break into a system and say, hey, I won't unlock this system until you give me a certain amount of Bitcoin. And so this is how, and so because of the fact that the blockchain is like open source and anyone can just like read all transactions that happen, it's very easy for you to track. It's very easy for someone to actually trace back who owns the wallet if you're not very careful. So that's why it's a good practice. Now the problem with non-deterministic wallets is that you'd have to create a whole bunch of private keys. Like I said, you'll have a bunch of seed phrases and you kind of have to keep that and remember them and back them all up. And usually people get lazy by the third, fourth, fifth. And so this is really bad. And it just increases the chance that you probably will get your money stolen. So this is really discouraged unless you're doing some type of test. And this picture kind of visualizes it where you just have a whole bunch of these keys. There's no relationship to them, just a whole bunch of different private keys. Now, a deterministic wallet, which is like the one we use when you create your MetaMask wallet, called seeded wallets, is where there's only one private key and then every other key that's related to it is derived from that one master key, right? And so this is why you can have a single seed phrase, but then with that seed phrase, you can create multiple accounts and everything. And we'll talk more about how that actually works. And the seed is like a randomly generated number, and that is combined with a bunch of different data. We'll talk about like chain code and even like a passphrase. And so you can use this seed to practically derive your private keys. So last week when I mentioned that, yeah, your private key is just your seed, it's like, yes, it is, but there's a little bit more that happens in the background, but essentially you can think of it the same thing. It's like your seed phrase is that master private key. And so the most advanced type of like deterministic wallets that are being used currently is hierarchical deterministic wallets. For the fact that I can't pronounce things, I'll just call it HD wallets. And so HD wallets have been defined by Bitcoin's BIP32 standard. And obviously you can tell Bitcoin is very popular whenever they're trying to create new crypto. But so it contains keys in like a tree structure. So this is kind of the idea of how you're actually deriving your keys from your seed. So you get your seed, you get that master key, which is really your private key. And then you can kind of and then that master key can have children, and then those children can have children. It's just kind of like a whole big family of keys, right? And so this is kind of like the really cool part is you can have all these different private keys that you associate with different reasons, but it's all derived from one seed, and all you have to remember is one seed. And this is really, really important in terms of user adoption, because it makes it a lot easier for kind of like the common person to be able to have different accounts. It's like, think of it like a bank account, right? With your bank account, you can open up multiple different accounts under it. You can have a savings, you can have multiple checkings and everything, right? But you only need to remember one password, one phrase whenever you're actually trying to access that account. So this is kind of how crypto makes that possible instead of you having to remember all these different passwords. So an advantage, like I mentioned, was that with this tree structure, you can use it kind of give different keys different meanings. So express organizational meaning, as in, hey, I want to use this key for, well, this, not specifically the key, but that key that you're going to use to derive a public your address is I want to use that address specifically for just when my friends want to send me money. I want to use when my family wants to send me money, when I'm getting paid, or yada yada yada. And also like you can extend this to more of like a corporate structure where look, you can have like, hey, if I say like Google's like, hey, Google has this one great master key, and then it derives another key for like YouTube, and then all its other different ventures that it has. So each of those different ventures can have their own kind of like associated private key that then is used to derive a public key and address. And so the second advantage is that you can actually create a public key that obviously corresponds to your address that is not at all tied to your private key. So that's really, really important because you can start to put your public key out there in kind of sketchy websites without really worrying about the fact that, okay, if they do figure it out, and even if they do decide to brute force and try to figure out what my private key actually would be, there is no actual private key to be associated with it. And that's because you can derive from your master public key, you can derive another public key that is then used to create your address. And so that's why I have it on here saying that you can use an insecure website as like a read-only, because there is no private key, you need your private key to send transactions and like sign those transactions. Because there is no private key, you can't actually send money using that wallet. Like that wallet is more, or that address is more of just receiving only, because you do have a place where people can send money, but you don't have a private key associated with it that you can, that you yourself can send money back to that person, whoever sent it to you. So some best practices, this is more in terms of like actually programming wallets, some of the standards that you will use. So there's standards that have emerged. Time has gone by, it's been like 12 years now. And so, but these standards are important, like I mentioned, for interoperability, which is really just saying, hey, like I mentioned, I think when we were creating our wallets, was that you can take your seed phrase, export it out of MetaMask. Let's say you don't like MetaMask, you're like, I want to use Coinbase wallet, or I want to use whatever other wallet that's out there. You can export your seed phrase from your MetaMask and then put that into your Coinbase wallet. And so that's what interoperability means. Just different wallets can all share like the same seed phrase. And then ease of use, really important for user adoption, secure and flexible, right? And the security kind of comes from the fact that you can have a public key that is not associated to your private key. And so the common standards that are used today are for your mnemonic words is BIP39, which we'll talk about more following this. And then your wallets, kind of like the whole general structure of your wallets, is BIP32. We'll talk a little bit about how this works, but whenever we start talking about multi-purpose wallet structures, where you really start to now get to kind of have that ability to have organizational meaning with your wallets and your different keys, that is defined by BIP43. And then when you're talking about wallets that can hold Bitcoin and Ethereum, that is BIP44. And so we won't cover that. I recommend it's a good read, but definitely not, we won't cover that today. So when we talk about mnemonic words are just like a sequence that encode a random number. And this is used to derive your seed, which is then used to kind of, it's really the base of your wallet, right? And this is like your backup, your recovery, like your password, the best way to think about it. And so these sequence of words are your backup. And if you do lose, like you could forget what you could lose your phone, you could, computer could break, but if you do have that seed phrase, you're still able to get back every single account, every single address that you have associated with that wallet. And that's kind of like the beauty of it. And so this is a bit of an example in terms of talking about like de-encoding what a mnemonic word actually encodes. So right here, you can think of this more as like your master key, right? And we'll talk more about why this is kind of false, but keep it simple. You can think of this as your master key, and then you'll have a phrase associated with this. And so it's just taking these different these hexadecimal values and associating it with a certain with an English word. And this is really, really important because I'm pretty sure I probably messed up when I was like copying that address down, or that hexadecimal. Like I probably mistyped something. I'm probably missing like an A or a B or something like that. But it would be really, really hard for me to write down, mistype or miscopy like wolf, juice, proud. Like that's a lot easier for people to actually remember. Because if you're told, hey, I need you to remember 32 these 32 numbers, you're gonna be like, okay, like I'm probably gonna lose it somewhere, or you're probably gonna mess up something you won't really notice. But if you misspelled a word, you misspelled insect instead of using an S, you use a Z. that's pretty easy for you to spot out. You'll be like, that's not an English word, at least you would hope, right? And so makes it a lot easier for people to actually be able to remember, store it a lot easier, and just kind of, even if you wanted to, you can memorize this. You really could memorize this. Don't really recommend, because you should keep it backed up somewhere offline, but you could memorize it. And so, like I mentioned, the BIP39 kind of defines the creation, and the creation is it like to actually create your seed phrase, create your mnemonic word, and then your seed phrase. This is described in 9 steps, kind of split into 2. And the first is generating your mnemonic words. And so number 1 is you kind of need that entropy, like we talked about with cryptography. You need to cryptographically generate some random numbers sequence of 128 to 256 bits, and it's an example right here is 128. But if you do 256 bits, you'll get to 24 words. And so the second step is you kind of create a checksum, and the easiest way to think about this, because even that wording confuses me, is that you're really taking a hash of what your what that random sequence of bits are, and then you're gonna hash that, and then you're gonna take like the first 4 bits, kind of like the really just follow the picture. This is the best way to do it. So you take that the first 4 bits, and then you add it, you append it to the end of what that sequence of random numbers are. I'm gonna call it S. So you append it to S, and so in our example, we're using 128 bits. So you add 4 bits to it, and you get 132. And then the fourth, I'm over here skipping. The fourth step is then you take S that you just appended, your new S, we'll call it S prime, and then you divide it into 11 bits, sections of 11 bits, right? And so this is how, and then those 11 bits are associated with certain words. So this is how we take, because this is in hex, so like this F has 4 bits right there, right? So you take 4 of that, and then like 1 strangle bit from that C, and then you can associate that with already like predefined, there's already like a predefined kind of dictionary that has 2,048 words, and so you associate those, and that's how you get those your mnemonic phrase. And so with that, you create the sequence of words. But so with your mnemonic phrase represents those bits just kind of reorganize, reshuffle, and everything like that. And this is then used with more entropy, kind of more randomness, that you create a 52-bit seed phrase. And this is through using a function called PBKDF2. Won't go into that because that's a lot more complicated than I need to explain. But so the second step of actually getting your phrase is you take the seed and you need to put into this function. So just think of it as like f of x, but it's PBKDF2. So you take that, and there's 2 inputs in it. One is just the actual like string, the word mnemonic. You'll have that, and then you also have an optional. They call it a salt. And so what this salt is it kind of adds extra security if you want, but it's optional. So it's just thinking of it as like it's another word that you can use that you append to mnemonic, but you don't even have to use that. So you take your mnemonic word, and then you take the salt, which is the phrase, which is just the phrase mnemonic, and then you kind of put this into the function, and then it'll spit out, like I said, it'll spit out really those 52-bit, that 52-bit those 52-bit value, right? And it's usually going to be represented in hex because it's way too long for that. And that bit value is going to be your seed phrase. Is there any questions?
Is the 52-bit value something else, or is that the 512-bit value?
Sorry, I said 52, I meant 512. Thank you for that. 512, there's way too many numbers today. Any other questions? Anyone keeping up? Okay, cool. So to summarize, you take this random 128 bits, right? Take random 128 bits, you hash that, you take the first 4 bits of those, add it to your S, which is the bits you randomly generated, and then you divide those into 11 bits each. Each of those 11 bits can represent a word, and all those words make your mnemonic word, right? And so then you take your mnemonic word, and then you put into another function, and you also add what they call salt. And so the normal salt itself would be your mnemonic, would just be the word mnemonic, and then you can also add what they call like a passphrase. That's optional, right? And then from there, you put it into PBKDF2, and then you'll get your actual seed, which is 512-bit value, which will be represented in hex. As a fun fact, so now that you have your seed, like there's two to the power of 512 possible seeds that you can have. which is ridiculous. Like, it's literally ridiculous. 10 to the power of 154. And the number of atoms, like I use this to kind of put in perspective just how many possible private keys you can make. This is like, what? I can't remember. It's like 5 times, 6 times the amount of possibilities compared to your private key. And so there's only about like 10 to the power of 80 atoms in the visible universe. So there's no way you're actually going to get the same seed phrase as someone if you use a good source of randomness. And then so if no passphrase is used, then the mnemonic is going to stretch. So essentially what that function is, the PBKDF2 is just taking your mnemonic word plus the salt and then stretching it out to an even longer 512-bit value. But if no passphrase is used, then you're going to get a consistent seed. So it's like every time you do that same process, you're going to get the same seed over and over and over again if you don't use a phrase. But if you do use a passphrase, then you add that to the function and you'll actually get a different seed than if you didn't use without it. Meaning that like this passphrase, again, it's optional. So it's more of like a second step, an extra password for you. And so this gives you even more possibilities of what seed phrase that you can actually use. And we'll go into kind of like the features and the risks, why it can be useful. And so you can think of this as like a second factor of authentication. So you know how you have 2-factor authentication where you put in your password, then you have to also use whatever, maybe use Duo or a text they text you a code or something. So you can think of it as that, right? So you have your original source of randomness which ends up being your mnemonic words, and then you also have the phrase, right? Because you're combining those. And so it's just another step for just in case someone wants to like steal you. Someone finds out your seed phrase, but if they don't know the passphrase, then they can't really use it. And then another thing is like you can use it as kind of like he says plausible deniability, which is really just saying like, hey, like here is my, this is actually a really dumb. It's a dumb example to me, but essentially what they're saying is you can give someone the wrong address. Because you can say, hey, this is the seed phrase, this is the passphrase I use, right? But if they don't know that passphrase, then they get led to a wrong wallet. So you can kind of like divert people into a different wallet by giving them the wrong passphrase. They still know your mnemonic words, but they don't know the passphrase, right? So that's that second factor of authentication. Someone may know your password, but they don't have your phone, so they can't log in. So it's kind of like the same thing right there. And so now, but there's a lot more risk to it, and so people don't actually recommend that you use the passphrase, because this is more for like if you have a lot of money in an account, maybe you do want to use it, but when you're creating your wallet, you weren't asked to do this. And so that's kind of like the general practice. And there's 2 reasons. One is if the person dies, the owner of the wallet dies, or they're unable to speak or anything like that, then you kind of lose the wallet. Regardless if they gave their child their mnemonic words, so they're practically the password to the wallet. Doesn't matter if they don't know the passphrase, it's practically useless. And then the second part is if you are storing your passphrase and your mnemonic words in the same place, it defeats the whole purpose. It's like, hey, here's my password and here's my phone. You have access to everything, right? So it defeats the purpose. So that's kind of the 2 reasons. It's more of like an extra step you can take if you want, but not recommended at all. Now, talk about if I didn't mention, if you just walked in, today's meeting is going to be short, so we're on our last part and we'll kind of just talk to each other. But so in BIP32 terminology, you can extend the keys, right? And so this is the whole idea of how we actually start to derive from our master key into different types of keys, right? And so you can extend from your parent to your child, and this produces the hierarchy of different keys and addresses. And so extending is really what it sounds like. You're taking that original key and then you're adding a chain code. And a chain code is a 256-bit binary string that is mixed with each key to produce, what does that say? Each key to produce your child key. So you're essentially taking kind of different bits of all the different keys and then making that to a chain code, and then adding that to the end. So you're kind of appending. I won't go into detail about specifically how the chain code works because that's not necessary to understand. But does anyone have questions about that? Okay, I'm making sense. I'm making sense through this. So that is what extending is. It's pretty self-explanatory. And you can, obviously, if it's that simple, you can probably start to reason about that. Hey, this is probably not the most secure way to actually derive these keys, because if I can just guess what the last part of the person's key is, then I can probably start to work backwards and figure out some things. And we'll talk about a better version of this. But if you ever are actually looking at, I don't know, your wallet, you somehow get down to lower levels where you're seeing the different addresses and keys, then you'll see that a private key, an extended private key prefix is going to have XPRV for private, and then an extended public key is going to have an XPub for public. So that's kind of the best way to think about it. And this image just kind of shows a good example. So you have your master private key, and with your private key, right, like we've talked about, you use hash function, and then you'll get your public key, and then from your public key, you can use that and create a derived child key. And that's just including the chain. So you're just adding that chain code to your public key, and then you'll get that new one. So this is just kind of visualize what it means by, you can take this extended public key and then you can start to create a whole bunch of different addresses. And so it just gives you the ability to organize these in different categories. Hey, I want BC1QD to be one that my mom sends me money for my birthday, but she doesn't because I'm too old to celebrate my birthday. And then last, so an alternative derivation function is called hardening. And so this kind of breaks the relationship between the public key that you use to derive. So you get your chain code from like that public key itself, like different public keys that you have. And so it breaks our relationship with it, because really, like I mentioned before, if you can understand that, hey, this is a derived key, and then you look at the last couple of bits, and then you can actually start to kind of piece things together to get the person's original public key, kind of work your way up that tree. And so a hardened key uses like the actual parent private key to derive the child chain code instead of using the public key. And so this is huge because, like I mentioned before, you can derive public keys. You can have this, if we go back and look at this chain, do I have it here? Oh, I think it's the next one. I don't have a good picture of it. I don't think I have a good picture. But in the tree itself, if you're all the way at the end, at the leaf of the trees, there is a lot of different derivations that happen where the private key is all the way at the top of that tree. And so you can't actually start to figure out what the actual private key is from the fact that you're all the way at the bottom of the leaf. And so if I try to explain this in a simpler way, is like, think about it is, you're able to actually use that public key on like a website, right? Like you're saying, hey, this public key is my address. And if someone looks at the last chain code, that chain code is derived from your private key. But your private key is all the way up at the top of the tree, that it would actually take a lot more brute forcing, and it wouldn't be a very easy way for you to actually derive what that private key is. There's a lot, just little steps I'm missing. I highly recommend you read the book. But does anybody have questions? Because I can probably specify anything I'm tripping up on. No? Great. So this is just did I skip some steps? No. This is just a good visualization of kind of what it is. So you have that, hey, you have your private key, this is the extended one. And typically you would actually use a hardened private key as like to get your master. And so get that, and then you can get your extended public key, and then you can create the children. But here, as it says down here, you cannot derive the public keys for the hardened child extended private keys. So just meaning that it's gonna be really hard for you to figure out what the previous public key was because you don't know anything about the private key. That is it, yes.
What was the book that you mentioned?
Mastering Ethereum. If you need it, message me on Discord because you don't have to pay for it at all.
Do you have like physical copies?
Do you have a physical? They might have a physical. I think you can order one if you like physical.
No, I
copies.
was asking what you're giving out. Are you just giving?
Oh no, I'm giving out digital copy. I don't have that many books. And that's everything. And so when it comes to what paths and bit 43 and 44 is to just kind of explain like different ways you would actually kind of how you would actually kind of know which part of the tree you're in. And so a hardened, so they use different they use like a range of numbers. So when you're talking about an extended, they use from like 0 to 2 to the power of 30. I think it's 31 or 32. It's one of those minus 1. They always take away 1, right? And so then your hardened is encoded with a number that is not that. It's 2 to the power of, I think it's actually 32. Yeah. And then to 2 to the power of like 64. So it's like they take this number and then let's say that this one actually gets you like 0x8000 something, right? And let's say your first hardened key would be actually identified by the last hex value there. So I know this is confusing. Let me start. So let's say you get your original seed. And then you get your first master. Hey, it's my master key, right? And so you're probably going to use a hardened, and so this is going to be the first number. It's going to be the first one, right? And then you take that and say, okay, I want to get a child of it. So then they literally just use a slash to tell you that, hey, I'm on a lower part of the branch, lower part of the tree, and then let's say you do another you do another hardened, and so this is the second hardened one. And it's just really identified like that. Does anyone?
Like, can you give an example like using MetaMask? Like, just math it real quick. Like, hey, we create our, I don't know, wallet on MetaMask, and which steps it goes through.
Okay, that's good. All right, so on MetaMask, well, essentially, because what MetaMask does, everything we just walked through is what MetaMask does in like the background.
Right.
It's like the background, right? So you get your original seed. Let's say it is, Texas blockchain, and a bunch of other different words, right? They have no association with each other. With that seed phrase, like I mentioned, let's go back up. With that seed phrase, you'll use the PBKDF2 function, and so it'll take this seed phrase, it'll use the salt of your the word actual mnemonic, and then that function will output along like actual seed, right? And so from that seed itself, like now that seed is going to be a really long like 2, 4, A, B, 3. Whole bunch, like really whatever 512 bits. I can't do that off the top of my head. And so from that itself, that is your like that you can think of. That's your seed. Sorry, that is your seed. This is your mnemonic, which is different than your seed. Your seed has to be created through using that function, inputting using mnemonic as its parameters and the actual mnemonic phrase itself, and then you'll get this seed value. And then from this seed value, you extend it. You take this whole thing. You use like the public key. So you can take this. So this would be like your private key in the sense, and then you'll hash it like we talked about last week. You'll get your public key, and then with that public key, you'll take some of the bits from it and then add it, and that's gonna be your chain code. And then you're gonna add it to whatever the public key file is. Let's say it's like x3, 2, 4, and then you add like your chain code. And this is going to lead to like that first master key. Does that make sense? I feel like I lost you.
Yeah, it lost me at chain code.
Okay, chain code comes from your public key, right? Your public key comes from your private key.
Right.
So you take, because I didn't even look too much into what the actual chain code is because the book doesn't go over that.
Okay.
But so your chain code comes from your public key. And so you take some bits from your public key, you append that to the original public key, and then you get what you'll call like your master public key.
Okay.
And then from there, you repeat that process over again. and then that's how you get the different children.
Okay.
And so so those children are encoded between these different values. So it's more of like, and so this would represent 0. This is that first part right here. And then let's say this is 0 and this is 1. Let's say, and then so you're practically saying, hey, I'm at my master right here. Number 1, I decided to go do this specific, I'm using this specific key. And then another one, I know this board is getting really messy. And then another one you say, hey, so like the different levels are indexed with 0, 1, and then you go 3. So you said, I decided to go to 0, 1, 3, and so you go here.
Okay, so you can use your, I guess, original seed to generate additional keys on Ethereum as well.
Yes, yes, that's exactly why I said I was answering your question today, because it's just depending on what type of wallet it is. If it's a deterministic, then you have to create a seed phrase for every single address. But if it's a non-deterministic, you have to create a seed phrase for every single address. But if it's a deterministic, then you can just use that and extend it and to derive different addresses and everything. Thank you. That was a good question, though. You guys just came, but we're actually like wrapping up today. Sorry, usually they're a lot longer, but today's short. But yeah, any other questions? I know that was really confusing.
Can you post this outro?
Yes, we always do. And that's why I put so many words on there. It's not because like can't really talk it through, but I just in case you guys want to follow it.
Just like an observation or analogy, this is kind of like DNA, where it's like you have like base pairs and then like code for a protein and stuff. I don't know, it's kind of like an interesting like, I don't know, parallel between like this and biology and stuff. I don't know, it'd be interesting if there's like any crossover.
There could be. There could be. Like, I don't know, they might even, because I know trees are used a lot in crypto, because it's easy, it's like an easy data structure to kind of keep things, so they might even use it in some software that they're trying to, so, but I don't know much about biology.
Is wallet creation recorded on the chain?
No.
So I could make my own mnemonic phrase, generate some keys that would work?
Yes, you could. You could do that all yourself, but the chances that you might generate some one that's already been used is higher if you're like decide to just randomly do that.
What if I generated one and I didn't use randomness? Is that possible?
Oh yeah, no, for sure. You could do this whole process yourself if you wanted to. You don't need to like. You would have to kind of like maybe you could import. I guess you could import that mnemonic phrase into MetaMask by saying like, hey, I've already created one and this is something I have. But you'd probably have to do a bit more lower level, actually interacting with the chain, like coding, to actually kind of putting your address into like actually being recorded. So what gets recorded actually on the blockchain is just your address. It's just like the address, the different addresses, not your private key, not your public key, but the address. Good question though. Try it out. Let me know how that goes.
I just want it to be like zoo, like 12 times in a row.
That would be pretty funny. Anyone else? No? Okay. With that being said, glad y'all kind of came through, a little bit more people, but I kind of just if